So for today's question, we're going to imagine we're running a marathon. And I don't mean running a marathon like we're running in the marathon. I mean running a marathon like we're organizing the race. That'll be the context for a fun little probability question that I originally got from a guy I used to teach with, buddy named Irv, shout out Big Irv. And the question goes like this. As the coordinator of this race, it's up to you to distribute the numbers to each of the different racers. So what you do is assign numbers to each runner. You start with 1 and the next person gets 2 and 3 and so on. So the highest number corresponds with the total number of people running the race. And you lose track of how many runners there are, but you're not super worried about it because you've implemented this system where a computer will track the numbers of the people that finish. And while it doesn't tell you each of the numbers individually, it tells you that the average of the numbers of the finishing runners was 604.2. Exactly. It also tells you that all but 2 runners finished and that those 2 non-finishing runners wore consecutive numbers. So here's 5 of the many runners in our race. And I know it looks more like 5 people posing for a picture pretending to be runners, not actual runners, but play along. Pretend these are 5 of the runners in our race. If, for example, this dude in blue wearing 820 was one of the non-finishers, that means the other non-finisher either wore 819 or 821. You get the point. The question is just which 2 runners didn't finish. I like this problem because it doesn't seem like there's enough information, right? I mean, if you told me how many runners there were, sure, I could figure it out. Or if you flip things around and told me the numbers of the 2 that didn't finish, I bet I could figure out how many total runners there are. But you're not telling me either of those 2 things. I'm not even sure how to get started. I'm going to use up one of my 2 Hector hints right off the bat.
Calculate averages in terms of n for extreme cases.
Okay, let me translate that a little bit. When Hector says extreme cases, what he's saying is, first assume that the 2 non-finishers wore numbers 1 and 2, and then assume that the 2 non-finishers wore the 2 largest numbers. Since we don't know the total number of runners, each of those will be expressions in terms of n, but Hector seems to think that's a good place to get started. To figure out the average of a bunch of numbers, all you gotta do is add them all up and then divide by how many you have. So if we assume that all the runners finish the race, all we'd have to do to calculate the average is add up all the numbers from 1 to n and then divide by n. To add up all the positive whole numbers from 1 to n, there's a formula you could use, but there's also a kind of cool little method that comes with an interesting story, so you can guess which way I'm gonna do it. Our story takes us back to Germany in the 18th century, where there's a child prodigy named Carl Friedrich Gauss. And no, this is not an incredibly high definition video from the 18th century of a young Carl Friedrich Gauss, but seeing a kid in front of some fake stock math background made me laugh, so I put it in. If you're curious, this is what Gauss actually looked like, but whatever. So anyways, Gauss was this child prodigy. There's all sorts of little anecdotes about how brilliant he was at a young age, and no one knows if any of them are actually true. But one of the more common ones dates back to when he was in primary school. The way the story goes is he was so brilliant he was kind of bored in class, and so a well-meaning teacher tried to give him some busy work. Supposedly, he was asked to add up all the whole numbers from 1 to 100. Teacher figured that would at least buy her some time with the rest of the class, but unfortunately, young Carl immediately told her that the answer was 5,050. The teacher was shocked, but when she checked his calculations, it turned out, of course, that he was right. How'd he do it so quickly? By using a method that some people today refer to as Gauss's method of addition. Here's the idea. Pretend you wrote out the sum, 1 plus 2 plus 3 plus 4, all the way up to 100. And then, instead of trying to add maybe left to right or something, you made a second copy of this sum. But instead of writing the terms of this second sum in increasing order like you did the first sum, you wrote them in decreasing order. If you lined things up just right and added vertically instead of horizontally, you'd come up with a third sum. But each of the terms in that third sum would be exactly 101. And since the columns of this little table that you've now created are numbered from 1 to 100 according to the first sum, we know that we have exactly 100 of these 101s. What's the sum of 100 101s? Well, that's just 100 times 101, in other words, 10,100. So that's the answer? No, that's not the answer. That would be the answer if you were adding up 2 of these sums. But remember, the original question was just looking for the sum of the numbers from 1 to 100. The answer to that will be half of 10,100, in other words, 5,050. But our goal isn't to figure out the sum of the first 100 numbers. It's to figure out the maximum and the minimum values of the average number that finished the race. To make that average as small as possible, we'd want to assume that the 2 runners with the largest numbers didn't finish. The 2 largest numbers are n, the total number of racers we have, and n minus 1. So if we wanted to add up the numbers of all the runners who did finish the race, we'd have to add up the numbers from 1 up to n minus 2. Even though we don't know what n is equal to, we can still use Gauss's method to figure out an expression for this sum. We need a second copy of our sum, written in decreasing order, lined up so that we can sum the columns. In this case, the sum of each of the columns would be n minus 1. How many columns do we have? Well, the first row of our little table numbers the columns from 1 up to n minus 2, so it looks like we'd have n minus 2 of these n minus 1s. But to get there, we needed 2 copies of our sum, so we'd have to divide this product by 2 to figure out the original sum. If the 2 runners that didn't finish were wearing the 2 highest numbers, then the sum of the numbers of the runners who did finish would be n minus 2 times n minus 1 divided by 2. To turn this sum into an average, we just divide by the number of runners who finished. N runners, 2 didn't finish, so n minus 2 did finish. Conveniently, the n minus 2's cancel, and we get n minus 1 over 2 as our minimal average. What about our maximal average, where the 2 non-finishing runners wore numbers 1 and 2? Well, we could use a similar method where we first figured out a maximal sum by using Gauss's method, but we could also be kind of clever and skip that altogether. Comparing the sum whose average we just calculated with the sum that we'd need to calculate if we wanted to figure out the maximal sum, you might notice that each term in the new sum is exactly 2 greater than a corresponding term in the old sum. So if I have 2 sets of equal size, and in the second set every element is 2 greater than a corresponding element in the first set, then the average in the second set will be exactly 2 more than the average in the first set. What I'm saying is the maximal average is just n minus 1 over 2 plus 2. Now we're getting somewhere. Recall that in our race, the average number of the finishers was 604.2. So 604.2 must be between n minus 1 over 2 and n minus 1 over 2 plus 2. We can get rid of the fraction by multiplying all 3 parts of this compound inequality by 2, and then recognize that n minus 1 plus 4 is just n plus 3, and break this up into 2 different inequalities. It's now easy to solve each inequality for n, and once we do so, we can put these back into a compound inequality to learn some information about n. And remember, n is the number of runners in the race, so n must be equal to 1206 or 1207 or 1208 or 1209. Shoot, I was kind of hoping this would answer the question. All we've managed to do is narrow down the number of runners to 4 possible options. Where do we go from here? I need some more help.
Rewrite your average as a mixed number.
A mixed number? Are you serious? Mixed numbers are the worst. They look like multiplication, but they act like addition. It's terrible notation, and I don't see how it's going to help anyways. But I guess I did ask for your help. So let's see, 604.2, I guess that 0.2 is 2/10 or 1/5. So the average number of the finishers in my race is 604 and 1/5. So when I take the sum of all the finishing numbers and I divide by the total number of runners who finish the race, I get 604 1/5. Aha! Hector, you're brilliant. The only way I could end up with that extra 1/5 is if the total number of runners who finished the race was divisible by 5. So n minus 2 must be a multiple of 5. Of the 4 possibilities for n, the only one that would leave n minus 2 as a multiple of 5 is 1,207. So 1,207 runners ran the race, meaning 1,205 of them finished the race because all but 2 finished. And since the average number of the finishers was 604.2, all I have to do is take that 604.2 and multiply it by 1,205 to figure out the sum of the numbers of the runners who finished the race. My calculator claims that sum is 728,061. Now I just need to know the sum of the numbers of all the runners who ran the race, and look at the difference to figure out who didn't finish. Hey Gauss, you mind figuring that out for me real quick? Thanks, bud. So now all I have to do is figure out the difference between this sum, the sum of all the numbers of runners who ran the race, and the sum I found earlier, the sum of the numbers of all the runners who finished the race. That difference, 967, is the sum of the 2 numbers of the runners who didn't finish the race. If m is the smaller of these 2 numbers, then m plus 1 is the larger of these 2 numbers. And if m plus 1 equals 967, then m equals 483. That means the 2 runners who didn't finish the race wore numbers 483 and 484. Ready for the challenge question? This one's a hard one. It's the same basic setup as the problem we just solved, except now we only give runners odd numbers. So the first runner gets number 1, the next one gets number 3, and then 5 and 7 and so on. So if we have n runners, the number of the runner with the highest number would be 2n minus 1. What we're told is that the average of the numbers of the runners who finish the race is 105.1. And this time, there's 3 runners who don't finish the race. Those 3 non-finishing runners all have consecutive odd numbers. So for example, 49, 51, and 53, or something like that. And the question is, what are the numbers of the 3 runners who didn't finish? As always, I'd love to see any thoughts, questions, or solutions in the comments.